Good afternoon students, welcome back to online maths class. So in the last class we have completed tangents and normals. So as exercise 6.4, that is approximations, have been removed from the syllabus. So I will be going for the next topic, and it is maxima and minima, exercise 6.5 introduction. So in this section we are going to make use of the concept of derivatives to find the points of maxima and the minima. That means at which point you are going to get the maximum value for a function and at which point you are going to get the minimum value of a function. So let us understand the maxima and minima. Later we will go for local maxima and local minima, and global maxima and global minima, or absolute maxima, absolute minima. So here I will consider two graphs. This is x, o, y, and then another one x, o, y. Then I consider this graph whose equation is y equal to f of x. So y which is equals to f of x, which is equals to f of x. And then, so here I will take this graph. So it is a parabola opening downwards, it is a parabola opening upwards. So here I take this point as C, and this as A, and this as B. So here this point is going to be C, and somewhere here this point is going to be this is A, and this is B. So now see here, at the point C you are going to get the maximum value of the function. At this point you are going to have the maximum value. So this value is going to be f of c. So this is f of c, whereas at the point C you are going to have the minimum value. This is going to be f of c. Now this is going to be f of c. So here by these two graphs, with the help of these two graphs, we can give the definition for maxima and minima. See here, at this point, that is you are going to have the value f of c. So f of c is going to be greater than or equal to f of x for all c belongs to, for all x belongs to a comma b. In between a comma b you are going to have f of c greater than or equal to f of x. So here f of c is greater than or equal to f of x. See here, if you take somewhere here and somewhere here, comparing these two values, this value is going to be greater. That is why f of c greater than or equal to f of x for all x belongs to open interval a comma b, open interval a comma b. And the point f of c, the value f of c is going to be maximum value, and the point c is going to be point of minima or minimum. So here f of c is going to be the maximum value, and then point c is going to be point of minimum or minima, point of minima. Are able to understand? Then now come to the second graph. At the point C you are going to have the minimum value. That minimum value we have denoted by f of c. So here f of c is less than or equal to f of x for all x belongs to open interval a comma b. So if considering these 2 points, so this value is going to be lesser. At the point C both the values are equal, f of c equal to f of x. That is why for the minima we are going to write f of c less than or equal to f of x for all x belongs to open interval a comma b. So here f of c is the minimum value and c is going to be the point of minima. So here f of c is the minimum value, and C is going to be point of minima or minimum. C is going to be point of minimum. So this is regarding the minimum and the maximum. Next we are going to discuss about local maxima and local minima. So that will be our next concept. Well, here local maxima and local minima. Local maxima and local minima. After this we are going to study about global maxima, global minima, or absolute maxima, absolute minima. So here again I will consider the same graphs. This is y, which is equals to f of x. X O x dash, and this is y O y dash. So here y equal to f of x. So now see here again I'll consider this point as C. This is the point C, and here this is the point C. So now at this point you are going to have the maximum value, that is going to be f of C. This will be f of C, and here this value is going to be f of C. So now I will consider a small positive quantity h which is greater than 0. See here, I will consider a small positive quantity h greater than 0. So now to the left of C we get C minus h. To the left of C, so it has to be C minus h, and to the right of C it has to be C plus h. To the right of C it has to be C plus h. So similarly here to the left of C it has to be C minus h, and to the right of C it has to be C plus h. So it has to be C plus h. So now this will be our C minus h, and this will be our C plus h. So now let us give the definition for local maxima and local minima. See here f of C is going to be greater than or equal to f of x for all x belongs to open interval C minus h comma C plus h. The meaning local indicates it is nearby. Locally you are comparing, not globally. You are just comparing this value f of C with these two. So for C the nearest values are C minus h, nearest points are C minus h and C plus h. So here also locally you are comparing, not globally. So that is why the name is local maxima and local minima. So now f of C, in this case f of C greater than or equal to f of x, for all x belongs to C minus h comma C plus h. So here where h is a small positive quantity greater than 0, then this implies f of C is f of c going to be, f of c is going to be the local maximum value, the local maximum value, the local maximum value, and the point C is going to be point of local maxima. At this point you are going to get the maxima. That is why C is going to be point of local maxima, point of local maxima. So now come to local minima. So compare nearby values, that is why the name is local. So here this definition can be written as f of c less than or equal to f of x, f of c less than or equal to f of x, because comparing to these values, this value is going to be minimum. F of c is minimum when you compare locally. So for all, so this is a symbol of for all x belongs to, for all x belongs to c minus h comma c plus h, then f of c is going to be local minimum value and c will be point of local minima. So here f of c will be the local minimum value, the local minimum, the local minimum value, the local minimum value. Next, what is C here? C is going to be the point of local minima. C will be the point of local minima, the point of local minima. So this is regarding the local maxima and the local minima. See here, at the point C, either you are going to have the local maxima or the local minima. Such points are called extreme points or the stationary points of the function. And then we will move on to the first derivative test. So we will discuss global maxima and global minima at the end. Well, now we are going to discuss about first derivative test. So every time it is very difficult to draw the graph for a given function and to identify point of local maxima and point of local minima. That is why we are going to give the working rule for the first derivative test. That means with the help of the derivative, we can find the point of maxima, local maxima, and the point of local minima. So till now we have not yet used the concept of derivative. Now we are going to make use of derivative to get the points of local maxima and local minima. So here again I will consider the same cases. So now we all know that this point is a point of local maxima, this point C. So here this point is point of local minima. So now let us draw the tangents for these two cases. So we can draw one tangent here, and then here also we can draw the tangent. So here also we can draw the tangents. Then similarly we can draw a tangent which is parallel to the x-axis, and then here we can draw the tangent, and here also we can draw the tangent. We can draw the tangent. So now whenever a tangent is parallel to the x-axis, then slope is going to be 0. This we have already discussed in tangents and normal introduction. When the line is parallel to the x-axis, then the slope of this line is going to be 0. What is the point here? It is C. That is why f dash of C is going to be 0. F dash of C will be 0. Similarly, this tangent is parallel to the x-axis. Therefore, the slope of this line is also 0. F dash of C is 0. F dash of C is 0. So now, what will be the slope of this line and this line? So here, this curve is increasing. So from this point to C, it is continuously increasing. Whenever the function is increasing, f dash of x is going to be greater than 0. We have discussed this in increasing and decreasing functions. And here, from the point to this point, it is continuously decreasing. This decreasing means the slope is going to be less than 0, or the slope is going to be negative. So here, we can write f dash of x greater than 0, and here we can write f dash of x less than 0. F dash of x less than 0. So this slope of this is going to be f dash of x greater than 0. It is less than 0. Similarly, we can write the slopes for this. So from C and to the left of C, close to C and to the left of C, see here the function is decreasing. If it is decreasing, then the slope is going to be less than 0. The slope will be negative. So that is the reason I am going to write f dash of x as less than 0. So here we can write less than 0. And then now close to C and to the right of C, the function is increasing. That means you are going to have positive slope. So here f dash of x will be greater than 0, or else we can also say in another way, that is m equal to tan theta. If you extend this line, so somewhere we get here, so it forms the angle theta. That means that this angle is an acute angle. Then acute angle means it is less than 90 degrees. That means the first quadrant. In the first quadrant, tan is going to be positive. So that is the reason we have written positive slope. And then here, if we extend this line, so you are going to have the obtuse angle with the x-axis. Obtuse means it is the second quadrant. In the second quadrant, tan is negative. That is why the slope is less than 0. The same case applies here. See here, if we extend this line, so you have obtuse angle. So obtuse angle means second quadrant, tan is negative. That is why the slope is less than 0 here. The slope is less than 0. And then, so here, extend this line, so you will have acute angle. Acute angle means tan theta is going to be positive. So that is why f dash of x is greater than 0. So this is all about the first derivative test that we have to write in words now. So now, so we can write the conclusion for this. Here, the first point is going to be, if f dash of x changes sign from, negative to positive, positive to negative as x increases through C, then C is going to be a point of local maxima. Are you able to understand? So see here, to the C and to the left of C, close to C and to the left of C, the derivative is greater than 0, and close to C and to the right of C, the derivative is less than 0. So here, for a point of local minima, close to C and to the left of C, the derivative is less than 0, that is negative. And close to C and to the right of 0, the derivative is positive, that is the greater than 0. So these 2 points are enough for writing the points. So here, if f dash of x, changes sign, ಹೌದ್ರಿ ಪಾಸಿಟಿವ್ ದಿಂದ ನೆಗೆಟಿವ್ ಚೇಂಜ್ ಆಗ್ಲಿಕ್ಕತ್ತದ ಇಲ್ಲಿ. ಸೊ ಎಫ್ ಡ್ಯಾಶ್ ಆಫ್ ಎಕ್ಸ್ ಚೇಂಜಸ್ ಸೈನ್ ಫ್ರಮ್ ಪಾಸಿಟಿವ್ ಟು ನೆಗೆಟಿವ್, as x increases through C, ಅಂದರೆ x increase ಆಕೋತ ಹೋದಂಗ್ರೆ as x increases through C, then C is a point of local maxima. Then C is a point of local maxima. And then f of C, this value f of C is going to be the local maximum value. F of C, and I'll write here, and f of C is the local maximum value. Local maximum value of f, the function. So this is the first point of the first derivative test. Now we will have to write the second point regarding the local minima. So here as the f dash of x changes sign from negative to positive, as x increases through C, then that point is going to be point of local minima, and f of C will be the local minimum value. Let us write that particular point now. Now I am going to write the second point. Well, let us complete the second point. If f dash of x changes sign from negative to positive, as x increases through C, then C is a point of local minima. And f of C is the local minimum value of the given function. F of C is the local minimum value of the function f. So these are the 2 points of a first derivative test, and the last point is going to be what happens if f dash of x does not change sign. So ee eradu case alli nodri illi ee point C left ge amele right ge f dash of x sign change aglikatav. So now what happens if the sign of f dash of x does not change? So that is going to be our third point. So that point is going to be point of inflection. So here I'll be considering a graph of the function x cube, cubic polynomial. X axis, this is the origin, this is y, x dash, and this will be y dash. So here y equal to x cube. I am going to draw the graph of cubic polynomial, y equal to x cube, and the graph is something like this. This we have studied in types of functions of our first PUC second chapter, relations and functions. So there he has given this curve. So y equal to x cube. So observe this graph. So it is continuously increasing from this point, it is continuously increasing, and at 0 again starts increasing. That means this function is not at all changing the sign of f dash of x. If you draw the tangent, so here, and we can draw the tangent here. What are the slopes? F dash of x greater than 0 in both the cases. That means at any point the sign of f dash of x is not changing. So that is why this point 0 is a point of inflection. This is going to be point of inflection. Point of inflection. So that we have to write in terms of words. So this will be the third point of the first derivative test. See here, if f dash of x does not change, if f dash of x does not change sign, if f dash of x does not change the sign, as x increases through c, as x increases through c, then c is neither a point of local maxima nor a point of local minima. ಅಂದ್ರೆ ಇಲ್ಲಿ ಈ ಪಾಯಿಂಟ್ 0ಕ್ಕೆ ನಾವು ಲೋಕಲ್ ಮಿನಿಮಾ ಅಂತೂ ಹೇಳಲ್ರಿ, ಲೋಕಲ್ ಮ್ಯಾಕ್ಸಿಮಾ ಅಂತೂ ಹೇಳಲ್ಲ. ಆ ಪಾಯಿಂಟ್ ಏನಾಗ್ತದೆ, ಪಾಯಿಂಟ್ ಆಫ್ ಇನ್ಫ್ಲೆಕ್ಷನ್ ಅಂತ ಹೇಳ್ತೀವಿ ರೀ. then c is neither a point of local maxima, nor a point of local minima, nor a point of local minima, In fact, such a point is called point of inflection. In fact, such a point is called point of inflection. That means whenever you have the point of inflection, you don't get any turning points. Turning points ಅಂದ್ರೆ ಏನ್ರಿ, ಅಲ್ಲಿ ಸೈನ್ ಚೇಂಜ್ ಆಗಬೇಕು, ನಮಗೊಂದು ಗ್ರೇಟರ್ ದ್ಯಾನ್ 0 ಇರಬೇಕಿಲ್ಲ ಲೆಸ್ ದ್ಯಾನ್ 0 ಇರಬೇಕು. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್, if you consider this, so here these are the turning points. At this point the slope of the graph is going to be changing. So here it is greater than 0, here it will be less than 0. So like this it continues. So these are the turning points. So in the case of point of inflection, we don't have any turning points as the function keep on increasing. That is why this O is going to be point of inflection. And one more note is there, can a function have more than one maxima or minima? So here in the beginning we have considered only two cases. So here this is going to be maxima and this is going to be minima. So here we have the graph of sinusoidal function, and these two are the maximas and these two are the minimas. Therefore a function can have more than one maxima and more than one minima. So this is all about the local maxima, local minima, and the first derivative test, where we are going to use the first derivative test to get the points of local maxima and local minima with the help of the concept of derivative. So this is all about the today's class.